Welcome to another instalment of quantum mechanics. Today we're going to do sections 36 through 38. We won't finish 38, that's going to be for the next class, which is this afternoon, which will be a lecture rather than a tude. So we want to give our final application of the general theory of angular momentum by considering the very, very important case of spin-half particles. We'll then move to the second last chapter of the course, where we consider central potentials, rotationally symmetric potentials, such as the 1 potential that surrounds a point nucleus in a hydrogen atom. We'll then consider using the Schrodinger equation and solving the Schrodinger equation in a spherical coordinate system to determine the energy levels of the hydrogen atom. Let's begin with spin-half, the final application of our general theory of angular momentum, or more precisely of Dirac's theory of general angular momentum, applied to the very important case of spin-half particles. I've said 3 times that spin-half is important. That's because it is. So many particles in physics are spin-half particles. Example, electron together with its antiparticle, the positron. We have a muon and an anti-muon. We can view the muon, by the way, as a heavy electron. There's a tauon and the anti-tauon, which we can view as a very, very, very heavy electron and anti-electron. There are the various neutrinos, the electron neutrino, the electron anti-neutrino. These are all spin-half particles. The tauon neutrino, the tau anti-neutrino, the mu anti-neutrino, and the muon, the muon neutrino and anti-neutrino respectively. Then there's the various quarks. We consider things such as protons and neutrons. By the way, they're spin-half as well. Proton, neutron, proton, anti-neutron, anti-proton. These are also spin-half particles. But in the standard model of particle physics, each of these is considered to be a composite made up of 3 quarks. What sort of quarks do we have? They're also spin-half particles. The up, the down, the charmed, the strange, the top, the bottom, together with their respective antiparticles, the anti-up, anti-down, anti-charmed, anti-strange, anti-top and anti-bottom. So there you go. There's 3, 12, 16, 17, 18, 19, 20, 21, 22. There's 27 spin-half particles, so they're kind of important, right? Now, ordinary matter is going to be made up of neutrons and protons and electrons. These neutrons and protons are going to be built up just of up and down quarks. But there's other particles in the known universe besides those which exist in stable atoms, and this gives you a flavour for some of them. There's things such as photons and gravitons. There are other particles which are certainly not spin-half particles, but a very large fraction of the particles known to physics are spin-half particles, hence this section is important. So we're applying our general theory of angular momentum. So spin is the angular momentum quantum number here. Spin is the general angular momentum quantum number, specialised to spin. The allowed values of the magnetic quantum number, which we call m subscript s in the present context, go from -s through to +s in steps of 1. So there's only 2 allowed spin projections for a spin-half particle, which we call down and up respectively. Now this is not down as in a down quark, this is down as in a down spin. Similarly, this is up as in an upwards projection of a spin-half, not as in an up quark. Now the allowed spin states, we use the spin wave function chi, which was an example of a spinner. And these are objects which have very, very interesting mathematical transformation properties, which are not intuitive at all. These things are not vectors. An ordinary vector, if you rotate it through 360 degrees, let me do that again. You take a vector, rotate it through 360 degrees, it's the same vector. A spinner, this looks like something with 2 components. looks like a two-dimensional vector, right? What happens if you take one of these things and rotate it through 360 degrees? It actually picks up a minus sign. You need to rotate it through 720 to come back to where you started. That's very non-intuitive. This is an example of a spinner. Anyway, we have these spinners. There's two of them. Yep, two spinners with spin quantum number and projection. The S here is a half, and the MS is plus or minus a half. So we've got two of these. And these two allowed spin states for a spin half particle we're going to call up and down respectively. So S, MS, where MS is pointing down, we'll just call this chi subscript down. And similarly for chi up. Similarly for chi up minus plus. And down is going to be represented by this, our two-component column vector. But I shouldn't call it a vector. It's not a vector, it's a spinner. It has this strange property. And up will be represented as follows. Now that strange property I mentioned, that you need to rotate a spinner through 720 degrees to get the same thing back again. If you want to see this viewed from a pure mathematics perspective, I recommend the book by Ali Cartan, the French mathematician, and the book is called The Theory of Spinners. All right, so we have these spin states, the spin half, chi up and down. Now, I mentioned earlier that when we developed the matrix theory of quantum mechanics, that this is one way of doing quantum mechanics. If you're talking about wave functions psi, which obey the Schrodinger equation, then you'd have the language of wave functions, which are functions of position and time, but position in particular, and a Schrodinger equation. On the other hand, you could have a matrix formulation of quantum mechanics, which we developed, where the differential operators, the linear differential operators, were replaced with matrices. When you're doing wave mechanics of psi of r's, wave functions that vary with position, you could do wave mechanics with your differential equations, or you could do matrix mechanics, or any one of any other infinite multiplicity of representations of quantum physics. With a theory of spin, however, because we can't think of spin as due to some literally spinning due to spatial extent in space, we can't have psi of r's for our spin wave functions. The point here is that a matrix formulation of spin wave functions isn't an alternative to the language of differential equations with spatial extent. You can't have the latter. The point is that it's very, very natural to use a matrix representation of quantum mechanics when considering spin. It's not the only way to do spin, but it's the classic and the most convenient way to do spin. So our various operators, Sx, Sy, Sz, S squared, and also the raising and lowering operators, S plus and S minus, all of these things are going to be represented as 2 by 2 matrices, and those are written down explicitly in equations 276 through 281 in the notes. And these things will have the usual properties. So for example, we know that S squared must act on the, let's say, on the up spinner, and what you'll get will be S into S plus 1 H bar squared times the spinner again. Yep. But S here is a half. So we should have this equation obeyed. You know, this is a 2 by 2 matrix. This is a column vector, more precisely a two-component spinner, and that should certainly obey this eigen spinner equation. It's not an eigenfunction equation, it's an eigenspinner equation, and so on. If you were to have S plus acting on chi down, it should raise it up 1 to chi up, and so on. So all of these properties that you would expect must be obeyed via the matrix representation of these operators, which are special cases of the formulae that we derived in an earlier class, acting on the two spinners up and down. Regarding wave functions, a spin half wave function, because we have both spatial extent in space and the spin, so-called degree of freedom. Yep. So here's an up spinner, but that spinner could certainly change with position in space. So here's a complex coefficient that varies with both position and time for the up spinner. Similarly, the down spinner, the spin degree of freedom, it can be smeared through space with a position and time-dependent coefficient. And we can shove these two things together into a two-component wave function. So when you have the theory of spin applied to a spin-half particle, then you actually have two complex wave functions, one for the up projection and one for the down projection. The magnitude squared of this quantity would be proportional to the probability of finding the electron at position r at time t with spin up. Similarly for the magnitude squared of the lower half of the two-component spinner. These two-component spinners are sometimes called, or often called, Pauli spinners by physicists, or we could call them two spinners or two-component spinners. Those terms are all synonymous. I also want to highlight exercise 64. Exercise 64, we introduce matrices that are proportional to the spin matrices with constant proportionality h bar on 2. So we have Sx defined as follows, and similarly for Sy and Sz can be redefined in terms of these sigma matrices. I suppose sigma is a Greek S and capital S is a Roman S. These sigmas are called Pauli matrices. And it should be no surprise that since the spin matrices obey a Lie algebra, so too do the Pauli matrices. That's written down in equations 284. The square of any individual Pauli matrix is a unit matrix. Now, showing that and proving that is exercise 64. I also want to point out equation 288. I'm introducing a new symbol here, which is the braces with two objects in there. First object, comma the second object. This right-hand side is the is the Kronecker delta, and I and j can be respectively. So I can be x, y, and z, and j can be x, y, and z. Objects in square brackets is what's called an anti-commutator. You can use this notation, or equivalently, you can use this notation, a commutator with a plus. These are two common notations for a so-called anti-commutator. And these things, by definition, instead of AB minus BA, which is a commutator, it's plus. And what this shows is that different Pauli matrices anti-commute. In other words, the anti-commutator is naught. Whereas if you have identical Pauli matrices, you'll get, for example, sigma x squared plus sigma y squared, which is 1 plus 1, which equals 2. That's what this thing says compactly. Anti-commutators, by the way, very naturally occur in the theory of spin-half particles, or more generally for half-integral spin particles, more generally for fermions. But this is a story for a later year course. That's all I wanted to say about spin-half. I now want to move on to the second last chapter of the course, which is also the last chapter that has specific mathematical physics content. This is chapter 7. So chapter 7 is on the hydrogen atom. And we're just asking the question, you've got some new fancy theory of quantum mechanics, your name's Erwin Schrödinger, it's 1925, you're working through for the stuff that's going to make your name, which you published in 1926. And you've got this new theory, and you want to ask the question, how do you solve for the energy levels of the hydrogen atom by solving the Schrödinger equation? Very natural question to ask, because you can do experiments which look at the spectral lines of hydrogen atom. You've got your Schrödinger theory, and you want to ask the question, what does the Schrödinger theory predict for the energy levels of the hydrogen atom? Now we want to address this problem in two steps. I first want to consider a more general problem. So instead of asking the less general problem, what are the energy levels of the hydrogen atom according to Schrödinger theory, I'm going to ask the more general question. I have some central potential, some potential, V, which depends only on radial distance r from some origin in spherical polar coordinates. This is a rotationally symmetric potential. This is what I would call a central potential. And let's consider what the Schrödinger equation looks like for central potentials. That'll be the topic of section 37. We'll then, in section 38, apply this to the specific case of the particular central potential associated with the hydrogen atom. So let's do it. I'm going to assume, by the way, that there's an implicit assumption here, which is that the nucleus is immobile, that it creates, that the source of the potential more generally is immobile, and it creates some potential that is a function purely of radial distance, r, from the origin, where the immobile potential is, to some particular point x. That's an implicit assumption. If you want to get beyond that assumption, it's actually surprisingly simple to do so. You introduce the concept of reduced mass, and the mathematics that follows is very, very similar. To avoid the slight complication of reduced mass, I'm going to assume, which is a good approximation, not a superb one, but a very, very good one, that the central nucleus, or the source more generally, of the potential is immobile. Yep. So we have a time-independent central potential. Now, even though we've been considering general angular momentum and the theory of spin, let's ignore spin for the purposes of this section, of this chapter. You don't have to, but let's ignore spin. So we're going to go back to ordinary scalar wave functions, where you just have one scalar wave function, psi of RT. Also, just because the potential is rotationally symmetric doesn't mean that the wave function is, so you need to be careful there. Even though your potential is rotationally symmetric, your Schrödinger equation, or the wave function in your Schrödinger equation, that will in general depend on x, y, and z. So I'm putting an r vector here. So let me write down the time-independent Schrödinger equation. Hamiltonian acts on wave function to give energy times the wave function. Or more precisely, this is the spatial wave function, depends only on spatial coordinate, lowercase psi. And the Hamiltonian here, which is just synonymous for the left-hand side of the Schrödinger equation for the purposes of this course, is this. Yep. V is the potential, but we're assuming that it's time independent and depends only on radial distance, little r from an origin. And there's a point of confusion now. We used m for mass, but m is now also the magnetic quantum number. So let me now put a little e subscript on that m to denote the mass of an electron, or any particular particle, but it's ultimately going to be an electron. So this is the equation we need to solve. Now, in second year vector analysis, you would have done the fun exercise of writing down the form of the Laplacian operator, which appears in the time-independent Schrödinger equation. You would have done the exercise of writing down the Laplacian operator in spherical polar coordinates. And there's a couple of different ways of doing this. I'm going to use this particular form, and I'll explain in a moment what I've written. And the first time you see this, it's a surprisingly complicated expression. So we're in spherical polar coordinates, r theta phi, and this is the Laplacian operator. Now, I note two things when I see this, or in fact, let me note three. This is an operator that acts on stuff, so you could imagine an operator, a function here, which the Laplacian acts on. This slightly peculiar thing, what's r squared d by dr? This is an operator, right? It acts on stuff. You could imagine a function living here, or equivalently a function living here, let's call it psi. Then you would have Laplacian of psi, and this term here would be psi dr, then multiply by r squared, then differentiate that product with respect to r, then divide by r squared. Similarly for this d by d theta and this d squared by d phi squared. A second thing I note is that this part depends only on r, and this part depends only on theta and phi. And the third thing I note, note is that we remember an earlier exercise when I asked you to calculate the L squared, the orbital angular momentum operator squared, in spherical polar coordinates. And what you learned was that L squared depend only on theta and phi. And in fact, you would have learned that L squared is proportional to this stuff in the braces. L squared on H bar squared is what's in the braces. So this simplifies our expression for the Laplacian considerably. Okay, so the R bit is as it was. We have a 1 on R squared, but we have L squared on H bar squared. So this is directly utilising a result of an exercise where you determined L squared in spherical polar coordinates, and you learned that up to a multiplicative constant, H bar squared, it had precisely this form, which depended only on theta and phi. So this is good. We can now use this result to write down our Schrödinger equation for a rotationally symmetric potential, for a rotationally symmetric time-independent potential. Yep. Kinetic energy term. This 1 on R squared is here, d by dr, etc. Plus the potential, sorry, plus this stuff, L squared on 2 me R squared, R plus V of R. And again, this is a rotationally symmetric potential. So all of this acts on the wave function, time-independent wave function, to give the energy times the wave function. Again, I note the wave function will in general not be rotationally symmetric, even though the potential is. I mean, think of water in a bucket, right? You could have or water in a pot. The pot is rotationally symmetric. The potential due to the pot is rotationally symmetric, but if you're boiling water in the pot, it won't necessarily be rotationally symmetric. In fact, in general, won't be. So this is the partial differential equation in polar form that we need to solve in order to get the energy levels of the hydrogen atom. Let me qualify that statement. We're actually not going to solve this equation. We're just going to get us far along towards solving this equation as we need to determine the energy levels. It'll turn out we don't actually need to solve this equation. We don't actually need to solve it in order to get the energy levels of the hydrogen atom. All right. Exercise 65 is to show that the Hamiltonian, the square of the orbital angular momentum operator, and its z component of the orbital angular momentum, that these things all commute. In other words, if you calculate the commutator of any pair of these quantities, you get 0. Therefore, bearing in mind the connection between commutators and an uncertainty principle, a special case of which is if two operators commute, their commutator is naught, then there is no associated uncertainty principle, and both quantities can be measured with arbitrary precision. Hence, the fact that these things all commute with one another means that you can form what are called simultaneous eigenfunctions, eigenfunctions which have a well-defined energy, a well-defined orbital angular momentum quantum number, and a well-defined magnetic quantum number. So the commuting of these three operators tells you that there exist wave functions with a well-defined eigenvalue of h, which is energy, eigenvalue of L squared, which is little l, and eigenvalue of Lz, which is magnetic quantum number. And these things are going to be simultaneous eigenfunctions of each of these operators, yeah, which means that if the Hamiltonian acts on that wave function, let me drop the functional dependence for clarity. Hamiltonian acts on this to give the eigenvalue of the Hamiltonian times the eigenfunction back again. Same eigenfunction, when acted upon by L squared, should pull out the usual factor times the eigenfunction back again. Lastly, similar thing for Lz. Good. So we have these equations here. Now we've seen a very similar set of equations before. In fact, when we were talking about spherical harmonics, we had this pair of equations, and we saw that the spherical harmonics obey this pair of equations. Now let me make a claim, which will be partially proved by me now, and partially proved by you as you work through the relevant exercises. So here's the claim. this simultaneous eigenfunction of L squared, Lz, and h can be written in a product form, which is a function purely of a radial variable, r, of the radial variable r, and some function of the azimuthal variables theta and phi. And this function is going to be precisely the spherical harmonic indexed by L and M that we met earlier. I don't know what this thing's going to be indexed by, but in general, it'll depend on all of these eigenvalues. So let me put all three as a subscript here. The claim is that this form, which separates, or more precisely, it wants to separate the radial dependence from the azimuthal dependence. The claim is that this thing is a way that you can separate, in the sense of differential equations, that you can separate the partial differential equation we need to solve. Now you show in an exercise that this thing will automatically satisfy these second and third equations. And the essential thing to note here is that each of these operators just depends on theta and phi. So as far as these operators are concerned, if you put this into either of these equations, the radial dependence isn't there. And so these things will just act directly on the spherical harmonics and pull out the same factor that you've seen previously when these operators respectively act on the spherical harmonics. But you show that explicitly as an exercise. You show that this form, this ansatz, satisfies these two things automatically. So we just have the question of what this equation looks like. What we're going to do now is to substitute this into here and find out that the angular dependence drops out entirely, leaving an ordinary differential equation involving just r. So let's do it. We want to substitute this into this. Yep. So left-hand side marches along, minus h bar squared on twice the mass of the electron, r squared, d by dr, etc. Then we have an L squared. By the way, I'm going to rub that off soon for reasons I'll justify. So I'm just writing out this bottom board here, plus our rotation symmetric potential, our central potential. And this is going to act on the wave function, which we're writing as a product of some function only of r times the spherical harmonic. By the way, I give this a name. I call it the radial wave function. So this is the radial wave function because it's a wave, or part of the wave function that depends only on the radial coordinate. Yep. All right. And that's going to equal the energy times the wave function back again. Now, this contains only angular coordinates. As far as L squared is concerned, this is a constant. L squared acts directly on the spherical harmonics. And we know what happens when L squared acts on the spherical harmonics. In fact, the spherical harmonics were constructed to be eigenfunctions of L squared and Lz. So when L squared acts on this spherical harmonic, it pulls out the associated eigenvalue, L plus 1, h cross squared. That's good. In fact, it's not just good, it's very good, because this whole operator now just depends on r. In fact, the only place that theta and phi dependence occurs now is, previously there was theta and phi dependence implicit in the L squared. That's now turned into a number. I can now cancel. And it's at that point that my partial differential equation has now become an ordinary differential equation for the radial wave function little r. So we started off with our full time-dependent wave function, right? Now that can be written as a spatial wave function times e to the minus iet on h cross. So you then have an equation which is a time-independent Schrodinger equation for the little wave for the spatial wave function psi. But we then write little psi as r times a spherical harmonic. And so now you have an equation for the radial wave function, which is this thing over here. So if you could solve for the radial wave function, you know what this is. You could throw it into this to get the time-independent wave function. You could then multiply by the usual e to the minus iet on h cross. Sorry, that's so messy. You could then multiply by the usual e to the minus iet on h cross to construct the wave function. There's going to be two more members in this sequence, just to warn you. All right, back to this. We have a differential equation for the radial wave function. But it's now an ordinary differential equation. There's only one variable here, little r. So these partial derivatives now become ordinary derivatives. Fantastic. So this is our radial wave function, the ordinary differential equation, obeyed by the radial wave function. And this is the thing that we need to solve, or that we need to consider. That's good. So this is equation 298 in the notes. Now, I don't like this equation because there's too many variables in here. There's little l's, there's MEs, there's energies. I ultimately want as few possible variables. We've already had this kind of logic when we were considering the simple harmonic oscillator. In order to get at the mathematical structure of the equation, or to make it as simple as possible, you want to reduce the number of free variables to the smallest number possible. Now, on the road to doing that, I want to introduce what's called the scaled radial wave function. Yep. So big R. Sorry, one further thing. This equation only has little l's, little l's in it, and an e. There's the little l, and there's the energy. The m has dropped out. So this tells us that r does not depend on m, so I can drop that. Yep. So we have our radial wave function, which depends on the radial coordinate. I'm going to scale this. If I multiply by little r, then by definition, so this is the radial wave function. By definition, this is going to be the little u, which is a scaled radial wave function. Yep. So little u equals little r times big R. So if you tell me little u, I'll tell you big R. You tell me big R, I'll stuff it into this and tell you little psi, which I'll stuff into this to tell you big psi. So we just keep boiling down the Schrodinger equation to something simpler and simpler, but we're making a change of variables at each stage. We now want to introduce this radial wave function. Sorry, scaled radial wave function. 1 point, since big R is little u on little r, little u as a necessary condition must vanish at the origin. Why? Because if little u didn't vanish at the origin, then when r equals 0, you'd have something that's non-zero divided by something that's arbitrarily small, making this thing blow up. So a necessary but not sufficient condition, a necessary condition for big R to not blow up when little r equals 0 is for little u to vanish. So I write it down explicitly. This thing must vanish. Must also vanish in a particular way, yep. Because when r equals 0, if this vanishes, you've got a 0 by 0, which you need to properly evaluate. For example, using L'Hopital's rule. But we'll return to the question of how this scaled radial wave function tends to 0 soon. Anyway, as an exercise, I ask you to show that if you make use of this definition of the scaled radial wave function, then this equation for big R becomes a new equation for little r. By the way, this is called the radial wave equation, or the radial form of the Schrodinger equation. We then transform it to the scaled radial wave equation. I don't like that terminology, by the way, because for me, wave equation means D'Alembert wave equation. To mathematicians, wave equation means D'Alembert wave equation. But physicists, with their crap notation, will call this, or can call this, the scaled radial wave equation. Terminology I don't like. Rotation symmetric potential, etc. Now, as I stare at this, something interesting occurs to mind. Scaled radial wave function, energy. Something interesting comes to mind. This has the structure of an eigenvalue equation. But it also looks a lot like the one-dimensional Schrodinger equation. In 1D, you'd have minus h bar squared on 2m, d squared by dx squared, plus the potential, acts on the wave function to give the energy times the wave function. So this, if we were in 1D, which we're not, right? This is an intrinsically three-dimensional problem, but if we were in 1D, then what's in the square box would be a potential. So we could call this an effective potential. Never forget the fact that when you have orbital angular momentum, then this is happening, right? Stuff is swirling. Okay, it might be probability density, but it's still swirling. And you know that when you have water swirling, for example in a pot or in a drain, that you have centrifugal forces which push the stuff out from the core of the vortex. When L equals naught, you have rotation. When L is non-zero, sorry, you have non-zero angular momentum. You have swirling. And this is... this term will then be non-zero if L is non-zero, and it diverges at the origin. In other words, the effective potential blows up at the origin, and that's going to exclude any wave function from the origin. All wave function will be excluded from the origin. If there's non-zero angular momentum, in some sense, probability density is being thrown out completely from the origin, r equals naught. So this can be called a centrifugal barrier, It's, by the way, why wave functions are zero at the core of a vortex. You saw that, for example, in the first assignment. By the way, I went to a talk yesterday on neutron stars, and I was very interested to learn that the same equation, exactly the same equation, the nonlinear Schrodinger equation, the Gross-Pidievsky equation, which we discussed in a previous tutorial, and which was the basis of the simulation in the first assignment, exactly the same equation is used to model neutron stars. I didn't know this. Neutron stars are very dense. I did know that they were so dense that they could actually behave as quantum liquids. What I didn't know was that the equation that describes a neutron star is exactly the same equation as was used to do the simulation for the assignment, animation, question 1. The nonlinear Schrodinger equation, the Gross-Pidievsky equation, and you see vortices, you see quantum chaos, fully developed quantum turbulence, except instead of a Bose-Einstein condensate, which is very, very small in size, I think tens of microns or tens of microns-ish, these things are 10 kilometres in size, described by exactly the same equation, and the vortices are 10 femtometres in size, which is insanely small. 10,000 times smaller than the width of a proton, that's small. And you have a precisely fully developed quantum turbulence in neutron stars. That's bloody excellent. Not only that, but by looking at the signals coming from neutron stars which rotate and radiate energy, which can be measured, you can actually correlate those measurements of neutron stars with simulations based on fully developed quantum turbulence, which is numerically modelled using the Gross-Pidievsky equation. So your Bose-Einstein condensates, there's 10 micron quantum clouds, very, very analogous. In fact, the mathematics is almost identical at one level to that which is used to describe neutron stars in state-of-the-art models. Very cool. That's quantum mechanics meets astrophysics on a cosmic scale. I'm still learning how to do the proper weight. It's like lawn bowls, not too much and not too little. All right. I've lost the track. I'm rebooting my head. We've got our equation. I've mentioned this idea of a centrifugal barrier, which also justifies the point, by the way, that wave function is in some sense pushed out of the origin. But we need to be a little bit careful. Little u is proportional to big R. And I mentioned earlier that little u must vanish. So here's an exercise, exercise 68. Little u must vanish at the origin as a necessary condition for big R to not blow up at the origin. But then you need to be more precise. How does it vanish at the origin? How rapidly does it vanish? So if we're going to take the limit as R becomes very small, but not infinitesimal, so maybe I shouldn't say this. I want R to be very, very, very small. Yeah? I'm being loose here deliberately. I want R to be small but not infinitesimal. How is this thing going to approach 0? And the claim is it's going to approach 0 as R to the L plus 1. Yep. And I want to use this later. So if little u is tending to 0 as R to the L plus 1, then big R will be tending to 0 as R to the L. So this is the radial wave function. as a function of E and L. If L is 0, then the radial wave function will... Actually, I don't care about L equals 0. When L equals 1, this radial wave function will behave as R to the 1. This is L equals 1. L equals 2, you'll have L squared. L equals 3, you'll have L cubed. L equals 4, you'll have L to the 4th. So what you're seeing here is that the bigger L is, the more it's doing this, the more it's actually throwing wave function stuff out, the more depleted the core of the quantum vortex is, and orbital angular momentum is a quantum vortex in a hydrogen atom. All right. Or more generally, in a rotation symmetric potential. Now that's all I wanted to say about the rotation symmetric potential. What I want to do now is to apply this to the special case of the hydrogen atom. So let's apply this to the special case of the hydrogen atom, and I won't get through all of this today. I should say that when I was an undergraduate, many centuries ago, I had this particular lecturer who used to cover themselves in chalk, and I used to laugh at this guy, and there's some sort of divine ghost who looks down on me and punishes me every lecture for laughing at the guy who covered himself with chalk, because I do it far worse than he did. All right, hydrogen atom, we want to specialise the case of the preceding discussions to the hydrogen atom. And again, we want to work out the energy levels of the hydrogen atom. If I had an extra 3 lectures, I'd also work out the wave functions for the hydrogen atom, but I won't. But I will tell you how you could work it out if you wanted to. We just want the energy levels. Now, for a hydrogen atom, the potential drops off as 1 on R. You know, hydrogen atom is just one immobile, positively charged nucleus. And you know, and this is a point charge, and you know from first year electrostatics that the potential drops off as 1 on R, and the field drops off as 1 on R squared. The latter, by the way, is Coulomb's law. So let's just revise this stuff briefly. The potential, as I said, drops off as 1 on R. The potential is going to be the product of the charges. You've got an electron with charge minus E. E is positive by definition for me. So minus the product of the charges, which will be minus E for the electron and plus E for the proton, giving a minus E squared. So that's the product of the charges on 4 pi epsilon naught R. So 4 pi epsilon naught R, epsilon naught being the permittivity of free space. So this is a 1 on R potential, which surrounds the point charge at the nucleus of a hydrogen atom. The negative here, which arose from the product of charges, which were opposite, negative E and plus E, also indicates that the potential energy of the electron is negative. If it wasn't negative, then the electron could escape to infinity and you wouldn't have an atom. So this negative potential of the electron, which is negative potential energy per unit charge, is indicating that the electron is bound. You also know that the force acting on the electron is the negative gradient of the potential. Now, since we're in spherically symmetric coordinates, you know that a negative gradient of a function purely of R will be minus the unit vector in the R direction times d dr. And I don't want vectors here, so I just want the magnitude of the force. So that gets rid of the negative sign, it gets rid of the unit vector. The magnitude of the force is going to be the magnitude of dv dr. And you can take this thing, it's something times r to the minus 1. You can differentiate to give something times r to the minus 2. Take its magnitude and you'll find that the force on the electron is, or the magnitude of the force more precisely, is given by Coulomb's law. The magnitude of the force is the product of the magnitude of the charges, E times E, electron and proton, over 4 pi epsilon naught R squared. So this is Coulomb's law, just making the point that this form of the potential, which goes into the Schrödinger equation, is consistent with Coulomb's law. Good. So we have our Coulomb inverse square force law. So we can now just substitute this particular form of the potential into the boxed equation in the top right board. Yep. to give the equation we need to solve, equation 305 of the notes. And I'm still unhappy, by the way, with how many constants there are in this equation. The potential, instead of V on R, is now a particular V on R, which is minus E squared over 4 pi epsilon naught R. That 1 on R potential I mentioned earlier. Then our centrifugal barrier term, which switches on when L is non-zero. And this all acts on the scaled radial wave function that depends on R to give the energy. And we want the quantized energies times the scaled radial wave function back again. Now, I want this square bracket to begin with d squared by dr squared. So what I'm going to do is to divide through every term by what I've just circled. Probably should have just written that down straight away. It's equation 306. Yep. So d squared by dr squared. Second order, ordinary differential equation. Notice how many constants are being clumped together here. This is a bunch of physical constants, but it all gets lumped into this one. That's suggesting that maybe some scaling could let me get rid of as many constants as possible to better see the mathematical structure of the equation. Here we have our centrifugal term. The energy on the right-hand side, I brought it over to the left-hand side. So this all acts on the scaled radial wave function to give naught. Now let me note that the energies must be negative. These are the energies of the electrons, or the energy of the electron. And the energies must be negative, because if they weren't, then the electron could escape to infinity and you wouldn't have an atom. So let's bear in mind that the electron has negative energy. And now I'm finally going to get my wish. I'm sorry, there's a open square bracket here. Now I'm going to get my wish. I'm going to scale this equation to get rid of as many constants as possible. Now the scaling that will make this equation as simple as possible is going to be obtained. I mean, you can just stare at it and then write down the answer. I would never do that. I would just keep trying changes of variables until this equation became as simple as possible. I'd begin, if I was staring at this cold, I need a new radial variable, rho. This is a scaled radial variable to be some constant times the radial variable little r. And I just try various things to try and make the equation as simple as possible. And I invite you to just do this cold rather than applying the scalings that I'm giving now. So here's the 8 times the mass of the electron. You want to just not get rid of constants, you also want to get rid of as many numbers as possible, that energy. And that's bad, that square root, because energy is negative. So this is going to be purely imaginary. I don't want imaginary scaled radial distances, hence the negative. So we introduce two changes of variables. Now this lambda is not the wavelength. It's just conventionally called lambda, so I'm doing that as well. This is not the wavelength. It's a bunch of constants. So we're putting the charge on the electron, or the magnitude of the charge on the electron, the pointless permittivity of free space. That Freudian slip was because the permittivity of free space has no physical significance. We have the mass of the electron. We divide through by twice the energy. Okay, so lambda is now going to be a function of the energy, as is the scaled radial coordinate. Negative because energy is negative. So this is the change of variables that we'll make. And with that change of variables, when you do exercise 69, what you'll get will be equation 309. And this makes me happy, right? D squared by d rho squared. Okay, you differentiate with respect to scaled radial coordinate. Okay, L's appearing, right? But you expect L to appear because the more it swirls, that should certainly change the scaled radial wave function. And so we don't mind the fact that the differential equation for UEL should depend on EL. Dependent variable rho, that's fine. one constant, that's good. I've got one constant, lambda, which is a measure of the energy. And okay, we've got a minus a quarter, we'll live with that. The point is that our equation is much, much simpler in form, and its structure is now more physically transparent. In retrospect, maybe what I said is rubbish. You can just stare at this and see the same thing, but we're trying to make the equation look as simple as possible. There's two variables here, little l and lambda. Now this is a thing that we want to solve ultimately. Where I'll begin the next class is the process of solving this thing as much as I need in order to get the required energy levels of the hydrogen atom. I'll stop there and thank you.